The basic refrigeration system has many uses, as seen at various points in this video series, from low, medium, and high temperature applications to the heat pump system. With the addition of specific accessories, and by making certain configuration changes, we were able to adapt the basic refrigeration system to perform a wide range of functions. We will now examine refrigeration as it is applied to the conditioning of air inside a structure, by first examining structural heat gain and its effects on the system. In the second part of this lesson, we will examine the effects of humidity on system performance and compare standard efficiency to high-efficiency air conditioning systems. In the warmer months, heat from outside the structure will leak inside, since the inside of the structure is cooler than the outside. Heat can enter by means of conduction, infiltration, and radiation. The rate at which heat enters the structure is related to the temperature difference between the inside and the outside of the structure. If it is 80 degrees outside and 80 degrees inside, there will be no infiltration because there is no difference in temperature. On the other hand, if it is 80 degrees inside and 100 degrees outside, heat will infiltrate the building. Heat can enter through the walls, windows, and doors. The rate of heat infiltration is increased if there is insufficient insulation in the structure or if the windows and doors do not make a tight seal. Air conditioning systems are actually high-temperature refrigeration systems that use the same four basic components: the compressor, condenser, metering device, and the evaporator. Two commonly encountered air conditioning system configurations are the package unit and the split system. Package units have all four of the system components built into the same cabinet. These units are often desirable because the system comes factory charged and no refrigerant lines need to be field installed. Supply and return ductwork does need to be connected to the unit, so it's typically located very close to the area being conditioned. Split systems are divided into two distinct sections, referred to as the air handler and condensing unit. The air handler is made up of the metering device, the evaporator coil, and the evaporator blower. In most cases, the control transformer is also located in the air handler. The condensing unit is made up of the compressor, condenser, and the condenser fan motor. The refrigerant piping from the condensing unit is connected to the air handler with two lines. The liquid line carries high-temperature, high-pressure liquid refrigerant from the condenser to the metering device. The suction line carries low-pressure, low-temperature vapor from the evaporator back to the compressor. The air conditioning evaporator is commonly found in one of three configurations. The A coil is constructed of two separate coils that are positioned to form the letter A. One of the main benefits of the A coil is that they have a larger heat exchange surface than a coil that is positioned perpendicular to the duct in which it is installed. The slant coil is a one-piece coil that is mounted in the duct at an angle. The angled coil increases the surface area of the heat exchange surface. The H coil is typically used for horizontal air handler configuration and is installed perpendicular to the duct. The condensate runs off the coil and accumulates in the can at the bottom of the coil, where it is then directed to the drain. When used for air conditioning applications, the evaporator typically operates at a temperature of 40 degrees. For an R22 system, the evaporator pressure would be about 69 psig. Inside the occupied space, the air temperature is approximately 75 degrees, with a relative humidity of about 50%. The air is reintroduced to the occupied space at a temperature of about 55 degrees, with humidity of about 95%. As the air coming off the evaporator coil mixes with the air in the occupied space, it expands and can absorb more moisture. resulting in the dehumidifying of the air in the space. The compressors used in air conditioning applications are the same types of those used in refrigeration applications, namely the reciprocating, rotary, scroll, and screw. Since the compressor operates the same for refrigeration and air conditioning applications, we will not discuss the operation here. We will, however, cover other compressor characteristics. Since compressors generate a great deal of heat, they must be cooled. Compressors can be suction gas cooled, air cooled, water cooled, and, in the case of the rotary and the scroll compressor, cooled by the compressor discharge gas. The compressor shown here is air-cooled and has ribs on the body of the compressor to increase the surface area of the pump housing. The function of the condenser is to reject heat from the air conditioning system. These condensers are typically air-cooled and constructed of copper tubes with aluminum fins. The fins are closely spaced to maximize the heat transfer between the condensing refrigerant and the air passing over and through the coil. Condensers are configured as either side air discharge or top discharge units. Over the past years, manufacturers have taken great pains in increasing the efficiency of air conditioning systems. One of the best ways to increase system efficiency is to lower the head pressure of the system. This reduces the load on the compressor because the compression ratio is lower. Standard efficiency condensers operate with saturation temperatures that range from 30 to 35 degrees higher than the outside ambient temperature. For an R22 system operating on a 95-degree day, this means that the refrigerant will condense at a temperature from 125 to 130 degrees and a pressure ranging from 278 to 297 psig. High-efficiency condensers, on the other hand, operate with saturation temperatures about 20 degrees higher than the outside ambient temperature. For an R22 system operating on a 95-degree day, means that the refrigerant will condense at a temperature of about 115 degrees and a pressure of about 243 psig. The thermostatic expansion valve and the fixed bore metering device are the most commonly used expansion devices on air conditioning equipment. The operation of these devices is the same for air conditioning applications as for refrigeration applications, but the temperature range in the thermostatic expansion valves is different. Air conditioning thermostatic expansion valves are at the high temperature range. One thing that should be mentioned at this point is that when TXVs are used, the system pressure does not equalize when the compressor cycles off, except when the valves are manufactured with bleed ports. For this reason, the compressor motor will require more starting torque. Here are the key operational points for an air conditioning system. The evaporator fan motor must be on when the compressor is operating. On systems without a low ambient control, the condenser fan motor should be on when the compressor is operating. The indoor fan should be able to operate continuously, even when the system is off. The compressor should cycle on and off to maintain the desired temperature of the occupied space. The thermostat in the occupied space takes care of most of the operational controls for the system. For example, the thermostat cycles the compressor on and off at the proper time, permits constant evaporator fan motor operation, and ensures that the evaporator fan motor is energized when the compressor is operating. Thermostats used on air conditioning systems are usually low-voltage devices. Before wiring the thermostat, be sure to check the equipment manufacturer's literature, as not all follow the same color-coding sequence. The control circuits used on air conditioning systems are typically low-voltage circuits that are powered by a control transformer that generates the 24-volt power supply at its secondary winding. The 24-volt power lead from the transformer is connected directly to the R terminal of the thermostat. while the common terminal on the transformer is connected to each of the loads in the control circuit to provide a complete current path when the devices are energized. The transformer produces the necessary power to energize the control circuit component, namely the coils of the relays and contactor. The contactor is one of the components in a control system that's used to control the operation of an electric load. Contactors cause sets of electrical contacts to open or close automatically to either energize or de-energize system load in response to the load requirement. The two main components of the contactor are the coil and the contact. The contactor coil generates a magnetic field, which pulls the contacts closed, energizing the system load that's being controlled. Contacts on the contactor are connected to an armature that helps ensure that all sets of contacts open and close at the same time. The contactor is used to control the operation of the system compressor and the condenser fan motor. The coil of the contactor is wired in series with the Y terminal on the thermostat. The relay is used to control the operation of the evaporator fan motor. The coil of the relay is wired in series with the G terminal on the thermostat. Other controls on an air conditioning system are used as safety devices and will prevent the system from operating if unsafe conditions exist. Such controls are the low pressure control and the high pressure control. Notice that the pressure switches are wired in series with the cooling contactor coil. If the system pressures are out of the desired range, one of the pressure switches will open to de-energize the cooling contactor coil. This will cause the contactor contacts to open, de-energizing the compressor. The Air Conditioning and Refrigeration Institute, known as ARI, has established a rating for design operating conditions. These conditions are an outside temperature of 95 degrees, an indoor temperature of 80 degrees with a humidity of 50%. These conditions provide a common benchmark against which all systems in the ARI directory are compared. In our discussion here, we will use an indoor temperature of 75 degrees, since it is more representative of actual operating conditions as experienced in the field. Let's take a look and see how changes in load and humidity affect system performance. Because the evaporator in an air conditioning system removes moisture from the air as well as lowering its temperature, the humidity level inside the structure will have an effect on the ability of the system to perform properly. If the outside temperature rises, the head pressure in the air conditioning system will rise as well. The temperature at which the refrigerant condenses increases, and the system capacity decreases. In addition, if the condenser loses its ability to reject heat, the system pressures and temperatures will go up. If the load on the house increases, the space temperature will increase. This increase in temperature will cause the refrigerant in the evaporator to boil faster, increasing the evaporator pressure and the superheat. As the load changes throughout the day, the operating pressures will change as well. Increases in load will result in an increase in the operating pressure, and vice versa. As we discussed earlier in this lesson, the head pressure on a high-efficiency system is lower than that of a standard efficiency system. But how can a technician determine if the system being worked on is high efficiency or standard efficiency? First, the technician should try to locate the paperwork that came with the unit. One of the most valuable pieces of information is the energy usage information, which compares the energy usage for standard and high efficiency systems and provides information for that particular system. If the unit is located toward the higher end of the scale, the system is most likely a high efficiency model. Equipment is rated by its efficiency ratio, originally referred to as the energy efficiency ratio, or EER. The DER is calculated by dividing the output capacity of the system by the power supplied to the system in watts. For example, a system that uses 4,000 watts of power to produce 36,000 BTUs of cooling will have an DER of 9.0. The DER does not take into account the cold coil that is left in the duct at the end of the cooling cycle. The seasonal energy efficiency ratio, or SEER, is a more accurate representation of system efficiency and takes into account the startup and shutdown cycle. One thing that manufacturers are doing to increase the efficiency of their equipment is to keep the indoor fan motor operating at the end of the cooling cycle to make best use of the cold evaporator coil. The government is encouraging manufacturers to increase the SEER ratings on their equipment to 13. There is also talk about making this 13 SEER minimum a requirement as opposed to just a recommendation. Second, high-efficiency condensing units are physically larger than standard efficiency condensing units. The increase in the condenser size increases the heat transfer surface, thereby reducing the head pressure and increasing the condenser subcooling. Third, high-efficiency systems permit the compressor to operate at lower amperages. Therefore, the amperage rating of the compressor on a high-efficiency system should be lower than that on a standard efficiency system. Fourth, the higher efficiency systems typically use a thermostatic expansion valve as opposed to a fixed bore metering device. Systems that operate with a capillary tube or orifice metering device are typically not high-efficiency units. When working on air conditioning systems, it's important to know the system supply voltage. Residential air conditioning systems are typically powered by 240-volt single-phase power, while some larger commercial equipment may be powered by 480-volt three-phase power. The nameplate on the piece of equipment provides the voltage at which the unit is intended to operate. The actual voltage supplied to the unit should be within 10% of the voltage indicated on the nameplate. Once the voltage supplied to the motor has been verified, the amperage draw of the motor can be measured and compared to the nameplate amperage on the motor. The current draw by the motor should be very close to the nameplate current. If the actual motor amperage is lower than the nameplate current rating, there may be a reduction in the amount of air that the blower is moving. A current draw that is too high is an indication that the blower may be moving too much air. On a blower system with belts and pulleys, adjusting the pulleys will change the amount of airflow, thereby changing the amperage draw